In this video, what we're going to do is calculate the extra energy an electron absorbs when a specific wavelength of light is shown onto a metal. And so the metal that we're going to be working with in this exercise is uranium, and uranium has a work function of 3.63 electron volts. The first step is that we want to convert electron volts into a more familiar unit such as joules. So to do that, what we will do is we will multiply 3.63 electron volts by 1.602 times 10 to the negative 19 joules. Divide that by 1 electron volt. What will happen is that the electron volts will cancel out. We will get that the work function is equal to 5.82 times 10 to the negative 19 joules. In this exercise, we're going to be shining 300 nanometer light onto that uranium surface, which, if we convert it into a more standard unit, is 3.00 times 10 to the negative 7 meters. To calculate the energy of the 300 nanometer light, we'll use the equation E equals hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. If we plug in the values, what we'll have is 6.626 times 10 to the negative 34 joules seconds times 3 times 10 to the 8th meters per second over 3.00 times 10 to the negative 7 meters. If we cancel out the meters and cancel out the seconds, what we end up with is an energy of 6.63 times 10 to the negative 19 joules. To determine the extra amount of energy that electron is going to absorb, we can subtract the work function from the energy of the 300 nanometer light. What we will get is a value of 6.63 times 10 to the negative 19 joules minus 5.82 times 10 to the negative 19 joules is equal to 4.8 times 10 to the negative 20 joules. And that is the extra energy that an electron will absorb from a uranium surface at 300 nanometers of light.